Two triangles are similar if they have the same shape. Well, all triangles are triangle-shaped, but that's not what we mean. If one triangle is a scaled-up or scaled-down version of another, then those triangles are similar. And when two similar triangles are the exact same size, they're congruent. To give a more rigorous definition, we need to use the word corresponding, which in our context means same relative position. In these congruent triangles, angle A and angle D are corresponding angles. They're both the largest angle in their triangle, and angle B corresponds to angle E, and C corresponds to F. When triangles are congruent, their corresponding angles are congruent, and their corresponding sides are congruent. Put more simply, corresponding parts of congruent triangles are congruent. This is such a fundamental truth of congruent triangles that it has a standard acronym, CPCTC. Corresponding parts of congruent triangles are congruent. When we write a declaration that two triangles are congruent, this is the symbol for congruent, we covered it in TR-03, we list the points so that the corresponding points, or equivalently angles, have the same relative position behind the triangle symbol. This might seem trivial, but triangles can be rotated or flipped and still be congruent, so it's a helpful convention to follow to keep track of what corresponds with what. When two triangles are congruent, there are 6 congruencies implied, the 3 angles and the 3 sides. Since the points are listed in corresponding order, the congruent sides can easily be identified since their endpoints are in corresponding position. So side AB is congruent to side DE, for example. In fact, when given a congruent statement, you don't even need to see the triangles to know the implied congruencies. Triangles with the same shape, but not necessarily the same size, are called similar. Here's the symbol for similar to. Triangle JKL is similar to triangle UTV. Corresponding angles should have the same relative position in similarity expressions too. Similar triangles will always have congruent corresponding angles, just like congruent triangles. For similar triangles, corresponding sides will have proportional lengths. For example, if segment JK is 1.4 times longer than segment UT, then KL will be 1.4 times longer than its corresponding side, TV, and JL will be 1.4 times longer than UV. We express the equality of these ratios like this. The ratios between the lengths of the corresponding sides are equal. Here's a summary chart. For congruent triangles, all corresponding parts are congruent, CPCTC. For similar triangles, corresponding angles are congruent, and corresponding sides are proportional. The proportional nature of similar triangles can be used to solve real-world problems. Here's a common trigonometry application. If we want to know the height of a structure such as a tree or statue or flagpole, but can't measure it directly, we can use similar triangles to determine its height. We find a nearby vertical pole, fence post, or other object whose height is known or can be easily measured. A yardstick or meter stick can be used, or even a person. We measure the shadow cast by both objects and construct triangles as shown. Since the sun's rays strike both objects at the same angle, and both triangles are right triangles, all 3 corresponding angles are congruent, so the triangles are similar. The lengths of the corresponding sides are proportional, so we can take the ratio between the 2 sides, h over 2.41 meters, and equate it to the ratio of these 2 sides, 1.80 meters over 0.4 meters. Isolating the variable algebraically yields the flagpole's height of 5.86 meters. That's the end of our 2-part review of triangles. For practice problems and drills, see TR-08X. In the next video, TR-09, we'll introduce the Pythagorean theorem.